The James Webb telescope has literally discovered a black hole 70 million light-years away, whose shock waves of gas and dust are upending our preconceived notions about the energy sources of active galactic nuclei. But what are some of the most potent spectacles that have occurred in the depths of the universe? Why do they contradict ICT's current models? And why could the mass monster still help us solve one of the biggest mysteries of contemporary space research? They are thought of as cosmic omnivores, massive machines of destruction that destroy everything in their path. But this is only half the truth about black holes. It is undeniable that the gravity monsters have the destructive property of irretrievably consuming everything that gets in their path because of their extreme compactness. But in order to understand what lies behind this frequently cited compactness, it is worth looking at the following example. The incomparably strong gravity that results from this means that nothing that has passed the black hole's event horizon can cross it again from the inside to the outside. No radiation, no information, and definitely no matter, but outside the cosmic death zone. This is the decisive factor. The strange objects behave like all normal massive bodies and can be easily orbited by other celestial bodies in unstable orbits. The diameter of a hypothetical black hole with the mass of the Sun would be 2.9 kilometers, and a black hole with the mass of the Earth would not even crack the 1 kilometer mark. Astronomers now believe that practically every galactic center is adorned by a supermassive representative of these cosmic monsters, and the Milky Way is no exception. However, even though supermassive black holes, which can surpass the mass of the Sun by a factor of millions or even billions, still pose many great mysteries to researchers, they are thought to play a fundamental role in the evolution of GXY. IES. The name of our central black hole is Sagittarius. It is a star with approximately 4 million solar masses. In a galaxy with the rather cumbersome name, the spectacular black hole that is presently making headlines in astronomy for its unexpected displays remains dormant. ESO IIO, a lecturer at Newcastle University, is a part of the G project, also known as the Galactic Activity Torus and Outflow Survey. As stated at the outset, this research partnership has recently made a groundbreaking finding while studying the nuclei of neighboring galaxies with the James Webb telescope. Around 70 million light-years separate Earth and the Galaxy of Desire, which contains an active, supermassive black hole at its core that ravenously devours everything in its path and emits intense light across the electromagnetic spectrum. The giant is able to provide itself with a rich galactic buffet that other black holes could only imagine. Let's take another look. Sagittarius. Because of the cosmic force diet, a star, in fact our black hole, is surrounded by so little matter that it's like a human consuming a grain of rice every few million years. Sagittarius. Therefore, a star is regarded as a quiet black hole if it has several noisy neighbors. One such neighbor is the supermassive black hole M87, which is located approximately 55 million light-years away in the center of the Aonomus galaxy, and is not only much more massive than Sagittarius. Supermassive black holes like the M87 star do not have the ability to passively wait to be fed. Rather, the extreme gravitational force of the colossus creates enormous tidal forces in the accretion disk, which causes the disk to heat up to 10 million degrees Celsius. Although a star with 6.5 billion solar masses is surrounded by a massive amount of gas and dust that continuously supplies the structure with new material due to its angular momentum, the matter cannot simply fall directly onto the star, but instead forms a swirling, flattened cloud of gas and dust, an accretion disk. Because of the tremendous heat, the accretion disk shines brightly, adding to the luminous display of the dynamic galactic nucleus. A shock forces astronomers to reconsider their strategy, but no matter how hungry a black hole is, the surrounding material does not all end up in its M. The strong magnetic fields direct some of the matter in the accretion disk towards the poles, of the black hole accelerating the charged particles to almost the speed of light from the two poles of the mass monster. This matter is in turn hurled outwards in the form of parallel jets that are also accompanied by emissions throughout the electromagnetic spectrum, especially radio waves, as a result of all these factors. Active galactic nuclei can be so bright that they outshine the light of all the stars in their home galaxy, but for all their radiant power, the pulsating hearts of galaxies were often invisible to telescopes in the past. This is because the dust that envelops the active galactic nuclei blocks our terrestrial view by absorbing visible light and other wavelengths of electromagnetic radiation. However, infrared light can pass through the veil of dust, and conveniently the James Webb telescope was designed specifically for infrared astronomy. With this in mind, the most powerful space telescope of all time is the perfect key to opening the door to the hidden centers of active galactic nuclei, and when the GATE team turned that key in the galaxy ESO. In other words, the experts discovered that the energy that heats up this swirling cloud of gas and dust may actually come from collisions with gas jets, and not from the supermassive black hole itself. As previously thought, the detection of such a shock structure came as a surprise to the scientists, to say the least, but it shows the enormous effects that the radio jets from black holes can have on their surroundings. The bottom line is that the dusty shock may also hold a much greater potential for knowledge. By studying the dust in the vicinity of supermassive black holes, experts could understand how galaxies recycle their material, and how exactly the gravity monsters influence galaxies in general. A central black hole rarely comes alone from ESO 428-434. Even though astronomers Bruce Beckey and Robert Hanbury Brown didn't actually know what they had found in the gigantic expanses of space, in fact, the experts only found an unnamed radio source in the constellation of Sagittarius, and it was only the series of observations over several years from the 1990s onwards that revealed this radio source to be a black hole. Now, however, it could be that the next cosmic revelation is imminent, because the latest data actually suggests that Sagittarius, a star, is not alone, but is accompanied by an extremely rare representative, a so-called intermediate black hole, in order to understand how such a giant can be detected. However, we must first remember that a black hole can only be detected via the gases orbiting its event horizon and its effect on nearby stars. The extreme gravity of the black hole accelerates the blazingly bright celestial bodies to record speeds and distorts their light, and strictly speaking, new stars should not even form in such extreme regions, as the gas clouds required for this would be torn apart in an instant. Well, that's what you would think at least, but in reality, the astronomers found not just one, but several protostars which, along with their dust cocoons, lie dormant in the immediate vicinity of Sagittarius AAR. The bottom line is that the stellar babies are only 1 to 0.3 light-year away from the black hole. But how did they manage to defy the Mercial conditions of their home? Well, this is precisely the question that the team led by Florian Pisker from the University of Cologne also addressed, in order to determine that IRS-13 is the densest and largest coherent structure in the near region of Sagittarius. The scientists examined the motion data of the star cluster, which is also home to the impossible protostars. The experts were to be given a major surprise by a star. Researchers discovered a disk-like system in the deeply embedded cluster after analyzing about 50 stellar orbits, which initially perplexed them. They also discovered that the stars in this cluster follow orderly orbits that cannot be explained by Sagittarius's influence. A star, alone in the same breath, IRS-13, also turned out to be much larger than previously thought. But what exactly holds the cluster together and influences the orbits of its stars? To find out, the astronomers also relied on data from the ELMA Observatory and NASA's Chandra X-ray telescope. And lo and behold, the data set showed that there is a zone in IRS-113 in which ionized gases orbit at high speed around an invisible center. According to Pizer, this suggests that a 30,000 solar mass intermediate black hole is hidden in the affected star cluster. This is a class of black holes that has hardly been researched to date and is considered a possible precursor to supermassive black holes in the case of IRS-13. The theory now states that the gravitational effect of the intermediate black hole holds the stellar association. Together and at the same time acts as a stabilizing antipole to the gravitational pole of the significantly more massive black hole, Sagittarius AAR. If the existence of Sagittarius A's stellar sibling is confirmed, space research would be enriched by an absolute sensation. For two reasons. On the one hand, intermediate black holes are extremely rare. The experts are now planning to test their exciting hypothesis in future observations. If you haven't already, click subscribe to ensure that you never miss another exciting video from us. The known candidates to date can be counted on the one hand, and on the other hand, they are thought to be a possible intermediate form between stellar black holes from supernovae and the supermassive formations in galaxy cores. It's possible that supermassive black holes are the result of the mergers of these intermediate forms. In other words, IRS-13 could harbor an essential building block for the growth of Sagittarius AAR.